And later, we have to monitoring and deploy our model. And finally, we have a step of knowledge.
Perdón, se cortó la transmisión.
¿Qué pasó?
Se cortó la transmisión, no sé. Gaby, ¿podemos como cortarla e iniciarla de nuevo?
Claramente no me escuchan. Ya inicié la transmisión otra vez.
Ok.
Gracias, lamento esto. ¿Puedes moverte a la diapositiva anterior y comenzar desde ahí?
Ok, sí.
Porque no sabemos qué pasó, que a los 26 minutos se cortó la transmisión.
Okay, so this one? Or
Yeah.
this one? From here?
From here.
Okay. So, sorry for the outbreak in the transmission. I hope it's not related to space weather. So, I know it's not. It's more probably to other problems. So, basically what I wanted to talk here is about data-driven modeling. And I was talking about that this data-driven models are not only machine learning, but also, for instance, other models such as data assimilation-based models. But we are going to talk about machine learning. And so I would like to just emphasize what are the differences between artificial intelligence, machine learning, and deep learning. So artificial intelligence is a complete area of computer science that emphasizes the creation of intelligent machines that work and react like humans. Machine learning is a subset of artificial intelligence, and the machine learning are methods of data analysis. And the idea is that this algorithm will learn from the data and we can find insights without explicit programming. So we get, these algorithms will learn from the data and we are going to get a model. And the deep learning is a subset of machine learning that is, that works with multi-layered neural networks. So it's a subset. What are important for machine learning? Data quality and quantity. They are very important. Quality is the best, the huge problem, because quantity, today we have a lot of data compared with before, So quality is very important. Another thing that the machine learning models are difficult to generalize, and it's difficult to validate and to establish what we call cost consequence from the data to the model. No? So to understand what is the model, or how the model arrives to these results, and to establish this consequence. So validation is very hard. Another thing that is many people are talking about is data science. Data science is not the same as machine learning. Machine learning is part of data science, or you can do data science without machine learning, but the usual data analysis tools that you know, but it's like a methodology on how to treat the data and how to extract data or knowledge from the data as an interdisciplinary field. And the idea is to transform the data into knowledge or information that aids decision-making. So it's like a conjunction of math and statistics plus scientific method plus programming. But has a lot, you have to have a lot of skills in programming and a lot of knowledge of technology. So I put here, there are more usual tools that you have to have, to understand, or to know, to do data science. And it encompasses a lot of different steps, important steps. And I put, this is my idea, let's say, a pipeline of many that can have, that first of all, you can have to manage the data. You have to clean, explore, wrangling, managing, and later on to storage appropriately the data, to then do the modeling. This is the part of the modeling. once you get the model you want, you have to monitor and deploy. And later on, you can have a decision based on this. So machine learning is in this step, in this part. And while you do all this, you have to have tools that help you to trace, to the traceability, to understand, to know what happens all the time with the data, with the code, and with the metrics you have. So when you are doing machine learning, you are not really doing data science. You have to do a little bit more. So I'm going to keep here the things here, and I'm going to be a little bit more fast here. So this is the modeling. And the model needs like these steps. So once you have the data already clean, already beautiful in your database, you have to take, or you have to serve the data into a step that is the preparation of the model. The model preparation includes something like resampling, sampling correctly the data, understanding the balance or unbalance of your data set, standardization, normalization, treatment of missing outliers, missing values and outliers, and transforming the data, because you will see that sometimes you don't want to have your data like it is, but you have to transform it, for instance, in a derived data, such as statistics, for example, and many other things that you have to do for prepare your data. Later, you have to choose what are the features for your model, and then you have to choose your model, you train and you evaluate your model, you predict or do inference, and you do all over again. This is an interactive part until you get the model you want, and later you have to the last part that's trying to interpret the results. So that's the complete idea of machine learning modeling. And I'm going to talk a little bit of machine learning for space weather. So as I said in the beginning, is that one we have to merge these two fields of research. So basically, what we have in space weather is a very highly coupled system, very different, difficult to understand, and has a lot of different time and space scales. So for instance, you know that in space you have astronomical units, you manage astronomical units. In the Earth, you manage kilometers and seconds, and it's a completely different scale. If we want to do it with a physical model, then you need to do a grid to develop your differential equations. Now you have two different grids for different scales, and you have to manage to couple this grid. So it shows you how difficult it can be. Another intrinsic problem of space weather is that the data is mostly unbalanced represented. What I mean with this, for instance, you know that you have very few extreme cases within a solar cycle. So if we want to learn these extreme cases, you have little information to learn from. So it's really tricky if you don't have much data to learn from. It's really tricky or difficult that the machine learning can learn it. It's really hard to model it. It's really hard. It's very expensive to run physical model, and this is why many are trying to do machine learning. They have a lot of physics involved and different kind of physics, but the other thing is that the data has bad quality, it's not standardized, and we have not enough data. There are many experiments that don't have a complete solar cycle of data, so we have not much data to learn from. That's the idea. And also the quality is not really good for machine learning, and we are doing the best we can, but it's we have yet not really good data. Standardization is a huge problem also. So here I put some of the many instruments that we can have in the Earth that can monitor the space weather. So this is a sounder, ionospheric sounder, and we have one here in Tucumán. This is a magnetometer. This is a GNSS receiver, and this is maybe all of you know, this is in Peru. This is an incoherent radar scatter radar. So this is all, and many more. This incoherent scatter radar is one of the, I don't know if the main or the most accurate system to observe the ionosphere, but it's so expensive that are really few. So that's the problem. The second best is the ionospheric radar, or the sounder, ionospheric sounder, and we have few also. But we have a lot of GNSS or GPS system, GNSS receivers, but are not the best. So it's like, this is less expensive. We have a lot, but it has less accuracy to observe, because this one is able, for instance, this radar is able to see all the vertical differences in the different region of the ionosphere, while this one is an integrated product. Okay, so in the group, we are interested in the effects on telecommunications mainly. It's not only the only case, but mainly we are very interested in telecommunication. Thus, we are very interested in the ionosphere. Here, I'm going to talk a little bit about two applications that we are working on. The first one is one by Tiziano Torres Peralta, one of our students, that is working on automatic calibration for some instrument. In this case, we are working on these Cherenkov, water Cherenkov detectors of asteroid particles of cosmic rays. And we have, what we want to do is, I will do it very briefly. The whole idea is that when a cosmic ray go through the atmosphere, it will collide with different species in the ionosphere, and will produce what we call a cascade, or a secondary cascade of particles that can be detected in these Cherenkov detectors. From the machine learning point of view, what we have is just particles arriving into our detector. And if we do an histogram of full charge, pulse charge, we can have, for different energies, we will have a count of particles. So we have this histogram, and the interesting that we have is to try to deconvolution this histogram and to understand which are the contribution of each particles. These particles are mostly muons, pions, and others, many more gamma. But we are interested in this one. This is what we call the hip of the muon hip. So this is something that we are interested in. So we make this model. This is an unsupervised machine learning to deconvolution this one, and to get this result, that is the histogram, all the convolution, and each of these is one kind of particle. But how can we go from this one to this one? Is when we use what it calls a clustering algorithm that is based on density. So if we do, in this case, we are doing a principal component analysis, and if we plot here, I plot just one component versus the other, so the first one versus the second one, and you will see here that this in this plot, if you see this, you will see that there are different densities, so probably they will belong to different particles. So we want to have algorithms able to see these densities. And this is one of them. So optics is able, through what we call a reachability plot, to get which are these groups, different groups of particles. So this is a work done by Tiziano. Is under revision. He just sent the paper. The idea is that we can use machine learning, since in space weather you are working a lot with the instrument, you can do machine learning for the instrument also. And now the other application is ionospheric forecast. So in the group we have a lot of instruments. We have 2 ionospheric sounders, one in Tucumán and the other in Bahía Blanca, 2 GNSS receivers, one in Tucumán and the other in Ushuaia. Tucumán is low latitude station. Ushuaia is high latitude station, almost high. We have a magnetometer, and we have a 3D Doppler system, continuous radar system. This is another radar, and a radiometer. So we have a lot of instruments. And we start working on trying to forecast the ionospheric conditions. But we are not interested in regular or different kind of perturbations in the aerosphere, but those that are related to space weather. So the first question we have to answer to us is that if we want to do the forecasting from a global, a regional, or local point of view, because scales are different, the problems are different, and maybe the phenomena are different locally. So we have to choose which kind of forecasting we want to do. In the group, we are doing many of them, but I'm going to show you the global one. Also, we have to take into account that the ionosphere has a regular variability, but we don't want to forecast the regular one because we know it. We want to forecast those irregularities that came from irregular variations, in particular because of space weather. So we have to choose the instrument. For a global point of view, we cannot use the radar, this radar that are very dispersed in the globe, but we have to use a derived data, that is TC, derived from GNSS. TC is the total electron content of the ionosphere. But the problem is that we know that we have a lot of data, we can cover the world, but we know the quality is not the best. So in terms of the modeling, we are going to choose our features. We know that for ionospheric forecasting, the perturbation of the geomagnetic field matters. We know that sudden enhancement in the solar radiation matters, and we want to learn or predict the behavior of the global ionosphere due to the space weather forcing. So we have to have an input that is related to the ionosphere and an external forcing from the space weather. So we choose TC as the input and KP as the forcing. The input is TC for 24 hours, and we forecast the next 24 hours of TC. We using a scheme that is called a NARCS that has the capability of analyzing or introducing external variables such as KP. Later on, we can discuss if KP is the best and why we are using KP index and not the others. So the problem is that we want to forecast this global TC, and we don't want only to use machine learning, but we want to enforce some constraints related to the physics, because we don't want only to go like black box, but we want to put some information about the physics. So I will show you how. This is a map of the station we consider. So the model works in two parts. The first part is to forecast single stations, and later we run a second part that extends the forecast to any location in the world. I'm not going to talk about the second part, and I'm going only to talk about the first part because it's related to machine learning. So now we are going to forecast for each of these stations. We plot our data. So this is a plot of a time series of one of the stations of TC. And what we see is that this is a behavior that is very, if you know a little bit of RTC, you will see and you will know what is happening. This is data set from 2005 to 2016. So we know that we are covering almost a solar cycle. So this is high activity years, and these are low activity years. So this is something that we want. This is related to the physics and related to the regular variations of the ionosphere. So when we have to choose how to train our model, we have to split the data very smart. Because if we split the data, for instance, as usual in machine learning, you split 80% of the data for training and 20% to testing, you will put here a division. And if you have this information trying to forecast this one, you have few samples of high activity and you are trying to forecast high activity. So this data, how important is to train this one. So we have to choose a smart splitting of the data, and is this one. So most of the data is used for training, a little bit for testing. This is a little bit tricky, but later on we add more data. I will talk a little bit more later. So the other problem is that we have to give food to the machine learning, two things, TC and KP. TC has a resolution from GIMAPS, we are using GIMAPS, of 2-hour resolutions, and KP has 3-hour resolution. So we have to try to have the same resolution in both. So we have to, in this case, we have an interpolation to have all in 2 hours resolution. There are no missing values, and this is why, because we are not dealing with the raw data, we are dealing with derived data that is modeled. So basically there are no missing values. Another important and smart decision is that we plot with the histogram of TC, of all the data we have. As you can see, this is not a normal distribution, but it's lagged. So we decide that the weights that we are going to give to to instantiate the machine learning should not be just random and with any distribution, but we want to have a distribution that helps us to learn from the data. So we choose another distribution. The other thing is that we are dealing with data with sequential data. So we are dealing with time series. So the order of the data matters. So as you know, if you are trying to forecast something in time series, it's really, really hard because usually we go to overfitting our data. So what we do is trying to have different models, independent models, to see if they are arrived to similar results. So we use 3 different methods, and we add 2 more. This is 3 machine learning, supervised machine learning models that are LSTIM, or low short-term memory, GRU, or gated recurrent unit, and CNN, convolution neural networks. But also we added what we call naive methods. I will talk to you a little bit later when we see the results. So we have here, these are the architecture we use. And when you have to model, you have to choose some hyperparameters. For instance, at the beginning, you have to choose how many layers you have to use, do you want to use, or you have to choose how many units will have for each layer, and so on and so forth. So any method can have different hyperparameters. So how to choose like the best ones? In this case, we run what we call a grid search, that is very brute force method. So we can improve this one. And we choose from this one, we choose this one, 5 hidden layers, the size of the batch is 16, and so the number of iteration of the model that crossing through all the train set is 20, and so on and so forth. So for each one, we have here, in this plot, you have the training. So we have the loss, which is the error of the training and the validation. Typically, if you're training correctly, the errors will tend to go together and maybe will like oscillate a little bit, but all together. So these are really good trainings. And seems to be bad, but you can see the scale. It's really nothing. The error is very, very short, very small and close. And you here is some station. This is station 9 and station 13. We plot here the worst and the best case, and both are good. So we know that we are training correctly. So this is something that is a hint that you are not overfitting too much. So we do the forecasting, and this is the next 24-hour. So we have trained the data sets, and the first 24-hour give these results. So LSTM, GRU, CNN, all the blue lines are the actual data, and all the orange one are the forecast. You will see the best and the worst and the bad ones. So in the best one, it's almost there, almost goes really, really, really good. But in the bad, you will see this kind of thing that are not that good, no? So we plot the errors, and we divide each station 1 to 18. We divide from high latitude, mid latitude, low latitude. So the errors itself are okay. With the references in the bibliography is similar errors, or this is a little bit lower errors, but we divide it by region, and we can see very clear that low latitude has the huge problem. Moreover, this one, the 7 one, you will see the first one, the blue, the orange, and the green are the machine learning methods, and you will see that these are the worst one. This station 7, number 7, is a station that is low latitude, but it's in the middle of the ocean. So we know that the data is bad. So we expect, this is the result that we expect, something that we know that should be like that. And these other two method that this one and this, the red and the purple one, are what we call naive methods. The first one is what we call frozen ionosphere. That is the idea that the forecast is going to be the same as yesterday, which is really bad. And the other one is just an average of the 27 days, the last 27 days. So there are basic statistics to compare. If we go further in the time, so if we start walking through the test set and beyond, we expect that the model start deteriorated because we learn from the previous data, right? So if we want to have better forecasting, we have to update the weights of the neural networks. So as expected, when we move forward, the errors start going bad. So bad that these are worse than the naive methods. So what we do is what is called incremental training. After after the first 24 forecasting, we take the last 24 previous one, and we update the weights. So basically what we are doing is having a new model each 24 hours. But the time of training is not different. It just takes 1 minute of a PC, a regular PC, to update all the weights, because we just see the difference. This is a paper that we have under revision, and we are working not only in this kind of, the results are really, really good with the training, the incremental training. You will see that the errors start going down, less than 2 tech units. So basically, we also analyze or try to forecast also regional ionospheric forecasting, do this. So it's under preparation, this one, so I didn't put here. This is under revision. And so we are tackling the both problems, the global one and the regional one. Not regional, really, it's not regional, it's local, really. Another thing that we have to think about, and this is another work we're working, this is a work by Eric, is a paper under revision also, about how to choose better the features. So as I tell you before, we are using KP index. Why didn't we use GST or other? So we put a lot of features, a lot of variables as external forcings, and we want to rank them or score them, which are the best. So we do a permutation feature importance, and we put for different kind of time lag, which are the best one. So in this case, we analyze different ones. This one here is what we call F10.7 flex solar. It's a solar solar forcing, let's say. Shows the solar, it's a solar flux. So basically this is not related to space weather, and thus we can see through the day has the same importance, right? And the others have different importance depending on the lag. I'm not going to go into deep on this one, but the idea is that we are going to shuffle all these features, and if one feature when we shuffle changes a lot the performance of the method, it means that it's important a lot. It's important. It has a lot of information. So we want to score better those that change a lot, have a lot of error when we shuffle them. The idea is to get better features. So why we want to have better features? Why we want to do better here? Because at the end we want to understand what is happening, and this is the problem in machine learning that is called explainability, and it's related with the trustworthiness. But because at the end, what happens is that someone needs to know how accurate or not a model is. And these models based on machine learning or deep learning are hard to understand, are not transparent at all. So basically, this machine learning or deep learning are very accurate, but less transparent. So we don't know what is happening inside. This is a nice plot of interpretability versus accuracy made by Barrera Arrieta 2019. I recommend it to read it if you are interested in this kind of thing. And as more transparent or more interpretable is the model, less accurate it is. So basically, there are a lot of methods to help in this case. We are working now, as a next step, on this idea of uncertainty quantification, and is on the way by Noelia. Noelia is one of our students, and she's working on Bayesian analysis for this. So basically, that's the idea. But in space weather, we don't only want to know about science, but also we want to go to operations at some point, or someone wants to go to operation. So we want to try to make this implemented in real time, no? So how far from this model I show you are we to the decision making? Well, we are very far. So this black box here is just the machine learning code, the modeling I show you. So there are a lot of things, technological or hidden technological depths that are related to this implementation in real time. Here's the paper, very interesting paper that I recommend to read. So what are the questions that we have to take in account? We want to know how easily can an entirely new algorithm approach be tested at full scale. So we want to change a little bit here, but not all the things here, and to test at the full scale. What is the transitive closure of all data dependencies? So this is very hard to do, all the dependencies in the data. How precisely can the impact of a new change in the system be measured? So before making a different model or any change in the system, we want to forecast how bad or how good it could be, or how much time it will imply or work. Does improving one model or signal degrade others? For instance, I show you many models in the same system. So if we change one of these, how will degrade the others? How quickly can a new member of the team be brought up to speed? This is very important if we are going to operations, because it should not depend on the person. It should be so stable that if anyone new comes, can manage to change things without changing all the whole system. So it's very hard to do. And we are very far for doing this. We are working on this, but we are not yet there. And my last slide, I don't know how much time I like to talk a lot, sorry for that. So my last slide has two things. For sure, open for question. And the other thing is that something that during the last collage, many students asked me is about material. And I put two links here. One is about this book that we wrote with three other researchers about scientific programming in Spanish, which can be very interesting for students that are not that familiar with English. And the other is this other link to the material that we posted there about the International Workshop on Machine Learning for Space Weather that we held in Buenos Aires in last November. Many of you attended, but if you didn't attend it, you can find the material here. So that's all for me. And this is a YouTube link to one of the talks of a friend that is Pablo Alcaín. He's talking a little bit, he's in PyCon in US, talking about software development for machine learning in Python. So if you're interested, you can watch it. So that's all for me. And I open to questions.
Thank you so much, Dr. Graciela Molina, for sharing your knowledge and taking your time for this talk. So now we are going to read the questions that you submitted. And I invite you to continue submitting questions if you have any. Yeah. So Ronald is going to read the question.
Yes. Thank you, Ivan. So we have a couple of questions. The first one is from Milo. He says, thank you, Graciela, for such an interesting talk. You mentioned the SW forecasting project was also implemented regionally and locally. Could
Yes.
you tell us a bit more about that part of the work?
About the regional local, yeah. We are working, yeah, exactly. I'm going back. Here. So here we are working on TC, as I mentioned before. So for the local forecasting, we are not using TC. We are using ionization data. More precisely F0, F2, that is the critical frequency of the F2 layer of the ionosphere. That is one of the parameters, more interesting parameters related to space weather, one of them. So we are using that data. The difficulty around this are that two main difficulties. There are many, but I will mention briefly two. One is the data. We acquire the data by ourselves directly from the instrument. So we are working a lot of time in cleaning the data to have this data set. So this data set is going to be unique. And related to this is a project that we are working with Chile in having quality data, data that is validated by interpreters, and is going to be used for the validation later. So this is very important and very difficult and time-consuming part. And the other thing is related to the physics, that when you have a local problem, sometimes, for instance, in case you have a low latitude station or under the equator or near the equatorial region station, you will have a lot of variability related to this, that are local variabilities of the ionosphere, and may like hide some consequences from space weather. So we have to think a lot about the physics, the local physics there. So it's very tricky, it's very difficult to do, and we are trying to add new instruments for this because it's what we need. I don't know if I answered you completely, or you want to know a little bit more.
Well, he has a second question also.
Yes.
Okay, I'm going to read it. Sometimes physics-based models help to improve forecasting performances. Do you see it feasible to include the physics of the photosphere and low corona in your forecasting models?
We have thought a lot about this. I have, the thing is, it's very interesting question. I will try to explain why this is important, because if we are putting some, we are working also with solar wind data. Solar wind data is acquired by, for instance, Discover, or one of these instruments in Discover that are very close to the Earth. It's L1 point. So it's almost there. It's almost here, and it's almost you can find that almost at the same time the perturbation that occurs in the ionosphere with the data in the solar wind, the measures in the solar wind. What happens? What happened is that we are able, with this data, we are able to see the development of the storm or the perturbation due to the storm, for instance, the main phase of the storm. But it's very hard to predict the sudden storm's commencement. And we are convinced that this is because we are not putting the solar input, no? And it's what we are talking about. So this is very important. There is a group in NOAA. You may have read something about Campo Reale. They predict KP, and they use some inputs from solar forcing. but we are not able yet to do it. So this is something that we want to do, let's say. So it's a very interesting point. Thank you. So at the end, yes, we should do this. We have to find the way. That's the answer, really.
Okay. Thanks, Graciela. So also Michael says thanks. We don't have any questions more. Any other questions? So
okay,
maybe we can pass to the last part.
Okay.
Yeah. So thanks, Graciela, again. With this, we come to the end of our meeting. We want to thank everyone who joined us. Thanks, Graciela, again for joining us on this first session. And finally, invite you to follow our social media at Interalage so that you can find out the next talks. Many great things are coming, and we want to share them with all of you. So thanks, and see you soon.